All right, hello and welcome back, guys. Today I'm going to be taking you through step by step how to build a roller coaster in preparation for the SAC. I've got here one that I've made as an example. I'm going to show you exactly how to do this, but essentially I'm using Desmos just to as a graphing tool, like you'll be drawing it on paper. I'm going to show you how I obtained all of the equations and all of the points on Desmos. It just makes for like a nicer graph than me doing everything by hand. I'm going to be using the CAS calculator for everything here, the spreadsheet function and so forth. I'd actually set up, before making this video, I did everything on the CAS calculator, and unfortunately the laptop emulator wiped it all, which is a real shame. Luckily you guys have your CAS calculators. If in case you're not aware, something that you can do on the CAS is save. So you can go file and then you can go save, and you can actually save your files as you're going through. But what I'm going to be using here is going to be the main function and the spreadsheet function predominantly here. So that's our example. And just as a quick refresher on it, the whole point of what we're doing here is we're trying to build a roller coaster cart that it's going to start at a particular point. So I'm going to give you initial condition. Here, the initial condition is 0, 25. The numbers that I'll give you on the SAC will be different, but I'll give you like an initial height and an initial slope of that graph. And you're going to need to come up with the piecewise defined function comprised of a bunch of concave up parabolas, such as this one here, and concave down parabolas, such as this one here, such that when the roller coaster starts out, it's going to come down here, it's going to come back up, it's going to reach a maximum height of no more than 5 meters per second. I'm going to give you that as the cap. And then it's going to keep going down here. Now, if the roller coaster is traveling too fast, then it's going to go up here, and maybe the roller coaster is going to come flying off and everyone's going to die, or it's going to come up here and it's not going to quite reach the top of this hill here, so it's going to roll back down again. So we can't have either of those scenarios. So we need to use an equation for velocity with consideration of friction. So the instructions that you get given might look something along these lines to start off with. So it'll just say, create a piecewise function for a roller coaster comprised of a minimum of 6 parabolas, given an initial height of, say, 25 meters. These numbers will be different for you. These are just the ones that I'm using for that example that I just showed you. You'll be given the vertex form of the parabola, and you'll be given the derivative for the parabola. And you're also going to be given this hideous-looking equation for velocity, and don't worry, you're only going to have to type this into the CAS once. After that, you can just copy it, and it should be fine. So you can see here this equation. What we need is the velocity. Before we get things going, we use the force due to gravity, and we look at the height. So this function here is the function for the height of the cart before a certain point and after a certain point. The equation will make sense when I show it to you given an example. Just know that the initial velocity of the roller coaster before it starts moving is 0, right? So we're up the top here. Roller coaster hasn't started moving. It's got a velocity of 0 meters per second. All right, so let's break down how we're going to approach this. So the very first thing that you need to do here is to come up with the equation for the first parabola. Now, the initial conditions that I've given you are essentially just that we have an initial point at 0, 25. So this would be the point, like on your graphing paper, you draw it up, you'd put 0, 25 up the top there, and we know some initial slope has been given to us as well. All right, so that initial slope in this example is negative 2.5, let's say. So we're going to start out looking at this. So we've got our equation for P1 of x is equal to, well, what is it equal to? Well, we're going to use this equation up here. So we can rearrange this and write it as, okay, our initial parabola is going to have to form a of x minus h squared plus k. Right now, we don't know what h or k are. However, we do know that this parabola, the way that we're kind of laying out this parabola is that the ground is actually the x-axis, right? So we don't know what this number here is. Obviously, I found it already. We don't know what our vertex for this parabola is going to be, given these initial conditions. But we do know that the vertex will occur on the x-axis. So that is to say that the height of the vertex, or the k value in this equation, is going to be 0. So right from the get-go, we know that, and this will be the same for you, the k for your first parabola is going to be 0. So we don't even need to consider that. So what we have here is a and h, just two unknown variables. All right. Now we've also been given a second equation. We know that it's that the derivative of this equation is going to be given by this second equation that's being given here, 2ax minus h. And it might actually be beneficial for you whenever you get given equations like this, to just straight away define them using the CAS calculator. The define command is exceedingly useful in this task. So it was action command define, and we can just define this as, say, f of x. So we're going to call it f of x is equal to a of x minus h squared. Let's just use that. You can then find the derivative of this using the keyboard. D dx like this. We just type in f of x, gives us the equation that's the same as the equation that's been given to you here. We could also define this as, let's say, g of x. So if we take that, we've now got our function for a general parabola and our function for a derivative have been defined for us. All right, so what do we know? Well, we've been given two initial conditions. These two initial conditions are that the roller coaster has an initial height of 0.25. So we know that it satisfies 0.25, which another way of writing that would be to say that the input, when we have an input of 0, we're going to get an output of 25 if I plug 0 into the equation for this parabola. And also we've been told that the slope at 0, the initial slope, is negative 2.5. And like I said, these numbers will be different for you on the task. But we can use this to set out a system of equations. So way that we could write this is we could write this as we're trying to solve a system of equations where these two initial conditions are satisfied. And the things that we don't know are a and h. So we actually have two equations and two initial conditions. And we're trying to solve for two unknowns. So we can use all of this. So the way we would do this on the CAS is we use this little function here, solving a system of equations, and we can just go ahead and type this in straight away. Like I said, we know that the function, so the equation for the parabola when f is equal to 0, is going to be equal to 25, and the derivative at this point, or the slope, when x equals 0 is equal to negative 2.5. And if I go ahead and type in here, we want to solve for a and h. It tells us that a must be equal to 1 over 16 and h must be equal to 20. So what we have actually obtained here is now the equation for this first parabola. So I'm just going to go ahead and write it in here to my document. So we now know that a is equal to 1 over 16, and we have x minus h squared. That's our first parabola. That should be fairly straightforward to find that. Oh, sorry, and 20. So h is equal to 20. There's the equation there. So we can go ahead and type this into our roller coaster over here. You would just graph this on your paper. We now know that, well, first up, if we think about this, if h is equal to 20, where does the turning point occur at? Well, that tells us that the turning point, or vertex, occurs at the coordinates 20, 0, because this is in the form ax minus h squared plus k. H is 20, k is 0, so that's the location of the vertex. So you would be able to draw this on your graphing paper. It's going to look like this. I'm just going to type it in. So we now know that p of 1 of x is equal to 1 over 16 of x minus 20 squared. There we go. There's our parabola. Starts at that point, passes through the turning point at 20, 0, and then it continues up here. So the next step that you're going to do when you're designing a parabola, and it's all laid out in the document on this website where I'm getting this task from. It goes through it in much more detail than I'm possibly going to do in this video. I'll try and go through it in full detail, but it also does the same thing. And I'm actually doing the exact same worked example that they give you. But once you've got that first parabola's equation worked out, the next thing we're going to do before we do the downward facing parabolas is we're actually first going to define the upward facing parabolas, the concave up parabolas. So what you need to do now is to choose two more points that are going to be the vertices of your upward facing parabolas, and you can actually place these randomly on the x-axis. You just need to think like, okay, we're trying to design a roller coaster here, so we can't have it too close to this first one here, otherwise it'll be too tight, but we don't want it to be too far away. You can sort of eyeball it about where exactly you want to put these. there's no wrong or right answer. It's just needs to be like a reasonable distance away from this first point. So the examples of the coordinates that they gave in this task were at 56, 0 and 84, 0, but you could have easily placed these at, let's say, like 40, 0 and 60, 0, or wherever you like, really. Yeah, I mean, you don't want it to be too close, but also not too far away. So approximate is fine, but you kind of, yeah, eyeball it. We know that the task, it's going to go up here and then it's going to go down there. You don't actually have to do this at this stage. You could do it a little bit later, but at some point you're going to need to place these vertices down. Anyway, the next thing that we're going to do is we're going to try and define what the equations of these parabolas are going to look like. So if we think, okay, this first parabola is going to go down here to 0, 20 and come back up. Next one needs to be at least 0, 40, maybe a bit further. So maybe as a rough estimate, you can say probably at least double the distance of this first one away, maybe a little bit further. Anyway, these parabolas should have the same width as this first parabola here. So the width of the parabola is defined by this this dilation factor, which in this case is 1/16, and the only other information that you need to define a parabola is just the coordinates of its turning point. So we know that the turning points of these by construction are going to be 56, 0 and 84, 0. So we can go ahead and immediately define these second two functions. So they're just going to be 1/16 x minus 56 squared, and p5 of x is going to be equal to 1/16 x minus 84 squared. Okay, so again, you could have placed these parabolas a little bit further or a little bit closer to that first parabola, but this is how you would do it. You just need to make sure that they have the same width as that first parabola. All right, so we've got those upward-facing parabolas sorted. We can kind of just go ahead and write those into our document over here. So we now have P3 of x is equal to 1/16 x minus 56 squared, and P5 of x is equal to 1/16 of x minus 84 squared. Okay, and it is going to be very convenient to define all of the parabolas that we're going to be using the CAS calculator's define function. Now, a quick note on how to do this. Once again, we can go action command define. We need to come up with unique names for each of the parabolas. What I've noticed is, given that we're going to be using the spreadsheet function, if you call them, say, for example, P1 of x, so maybe I'm going to call this first parabola that I just found up here P1 of x. So that has the equation 1/16 x minus 20 squared. If I was to do that, we're going to have an issue when we come across to the spreadsheet function over here, because if I was to type in, say, P1 of 3, it presents me with an error. It says wrong argument type. The reason it's doing that is because it thinks I'm saying cell P1, because this is like an Excel spreadsheet over here. So we can't just call it P1. We have to come up with a more unique name than that for it. So instead, what I've been having success with is calling my first parabola PAR1. I understand typing using the CAS is a bit tricky, but you need to come up with some name like this. So let's say we call PAR1. Then if I go back over to the spreadsheet function, that shouldn't have any issues anymore. There we go. So it can calculate using that function. So what I've done is, once again, to recap this, I have defined the first parabola PAR1, and I've already found that equation. That was what I did on this document over here. And we can just do the same thing for our other parabolas. So we can define, and I should use the commands here. So we go action command define PAR3x is equal to, and you can use copy paste if that saves you the time. So we can go edit, copy, edit, paste. There we go. And then we can define PAR3 as that 56 squared, because that was what we were using for our second turning point there. And in the same way, we can just go ahead and edit, highlight all this, copy the same line, edit, copy, edit, paste, because the equation for a parabola 5, it's exactly the same, except the turning point's occurring at 84, 0, so we can just define it like that. Awesome. So we've got our parabolas defined over here. What we're also going to be needing to use for our calculations is the derivatives of these parabolas. So first up, let's go ahead and define those. So if you don't remember, you can find the derivative of an equation of an equation using the ddx function here. And if you just type in PAR1, so parabola 1, and hit enter using the ddx function, it tells you that the derivative is x minus 20 over 8. Now I'm going to need to define all of these derivatives as well for our simultaneous equations purpose. So to do that, once again, we go action command define, we type in derivative 1x is equal to this, and that's just telling me that the equation for the derivative of the first parabola is this. And I'm going to do the same thing for the other parabolas. So first up, find the derivative of parabola 3 and define that as derivative 3 of x is equal to that. And I want to find the derivative of parabola 5. And then I'm going to define that as the derivative 5, like so. All right, beautiful. I've got them all laid out there. All right, now we need to do the tricky part. So next thing we're going to do is start finding the equations of these downward-facing parabolas. Now this is where we're going to have to start using this this equation for velocity. So we're going to start up here, right? That's our first thought. We're going to start up here. We're going to come down here. We're then going to reach a certain height, right? And then we're going to then transfer across to this other parabola that's over here. But like I said before, we need that height to be a certain point where it's not too, like where the velocity of our cart isn't going too fast, because then we're going to fly off and die. And we also don't want to go up here and then we slow down to a point where we roll backwards, come back down here. So we need our velocity to be a positive number going forward over here. So this is where we're going to use our velocity equation. And this is how you're going to find that value here. First thing that you might want to note before we go about finding that is what we do know about the second parabola. So we can even start defining it. What we do know about this second parabola, so I'm going to start defining parabola 2. Well, we know that it's the horizontal position of its vertice is going to be exactly halfway between the two turning points of the two neighboring parabolas. So if we think about it, right, this parabola here has a turning point at 20, 0. This one has a turning point at 56, 0. So we can find the average of those two numbers, 20 plus 56. So to find the average, the midpoint of the two numbers, you add them together, divide by 2. The midpoint of those two numbers is 38. And you can see here, that's where the two parabolas cross over. It's the midpoint between the two. So we know that the height of this parabola is going to be 32. So we can first define that component of it. We know that even if we don't know what the value of k is, we don't know what the vertical position of this turning point is, we know that its horizontal position is going to be negative 38, and we don't know what the value of a is. So we can define parabola 2 partially like this. But let's get back to the spreadsheet function now. All right, so in order to find the point where the velocity is approaching 0, this is how I want you to lay out your spreadsheet. And there will be scaffolding for this in the document, a little bit better than in the in this document here that we were looking at before. So the first thing we're going to need to use is this equation here. And here's how I want you to lay out your spreadsheet. We're going to have column A is going to be our x coordinate. Column B is going to be the heights of the roller coaster at a particular x coordinate. And column C is going to be the velocity of the roller coaster at that point. To start out with, we can just list these out as integer values. So we can see that, we're not even going to start slowing down. We're going to reach our maximum speed at the bottom of the parabola here, and then we're going to slow down coming up here. So we need numbers all the way up to at least like 30 or so, something like that. So we can type these in. So one way we could do it is we could just type these into column A. But that takes a bit of time. So you can use an iterative method here. So for example, if I was to define this one here, what you can do is you can go edit, fill, get rid of that, edit, fill range. Okay, what we're going to do is we're going to define this cell, A5, as being equal to A4 plus 1. So the previous cell plus 1. Here's how that would look like if I was to say this cell here is equal to that plus 1, it just adds 1 onto that. But I want to copy this and I want it to fill for a bunch of different values. So we go edit, fill range. We have this rule. This first cell here, A5, is going to be equal to the previous one plus 1. And we want to continue this pattern for a certain number of x values. So let's say we want to go all the way up to like x equals 25 or something. What we can do here is type in this colon and then go capital A 25, and that's saying we're going to fill in the range from A5 all the way up to A25 using this same formula. So we type that, and you can see that now this first column is numbers going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 24. Okay, that's good for now. We can add to that later. All right, second cell. We want this column here to be the height of the parabola at all of these different values. So if I was to go, and again, I've already defined what the, back over at the main screen, I've already defined my parabola 1. So I've defined it as being equal to the equation that we now know is parabola 1. So what we can do is in this second cell is we can say this cell is going to be equal to parabola 1 with an input of this cell here, the one that's right next to it. Okay, works. And once again, if I don't want to type in this command every single time, by the way, we should probably start at 0, shouldn't we? So 1, 2, 3, 4, 5. That's better. Okay. We want our numbers to start at 0. Why do we want our numbers to start at 0? Well, because we need to consider an initial velocity of 0. So yeah, we do need to consider when x equals 0, the height is equal to 25. That was what we were given initially. Okay, let's do this again. So at x equals 1, what is the height going to be equal to? PA1 with an input of A3 is equal to 22.56. Does that match up with what Desmos is telling us over here or what your graphing calculator would tell you? Well, when x equals 1, we're seeing that, yeah, it is 22.56, which is what our CAS calculator is splitting out over here. So we're just getting the corresponding y value for that x coordinate. Let's repeat this process up to cell 25. If I go here, edit, fill range, I want B3 to be equal to parabola 1 with an input of A3. And I want to repeat this process all the way up to B25. Okay, so there are all of the corresponding y coordinates up to this point. You can see that, for example, when x is equal to 20, h is equal to 0. Okay, finally, in column C over here, we need to type out that hideous equation. And like I promised, we only have to do this once, but just be really careful when you do that you don't make a typo, because that will cause issues. Let's just close this. Okay, that's right. All good. Well, you're seeing that specialist exam there. That's all good. Getting back over here. Okay, so we're going to define the velocity given by this formula right here. Let's be careful when you're typing this out. We go keyboard, we go square root, and we're going to type it in. Notice that the way that the spreadsheet function works is it's a bit wrong here. Oh, by the way, before we start doing that, we should define our initial velocity. The initial velocity is 0. So this is something that will be given to you in the question. Assume that the initial velocity is 0. So when x equals 0, v is equal to 0. And that's important because in this equation, we actually need to know what the previous velocity was. That's right here in the equation. So we need to have the previous velocity. So once you've typed in that first row basically as is with your given initial condition of the height, we type in equals, we type in this square root function, and just notice that the way it works is we have the square root function. The brackets indicate what is going to be square rooted, so just be really careful when typing this in that you close brackets after your overall argument, but it's going to be equal to the previous cell, so in this case C2, squares minus 2 times the force due to gravity, which is given here as 9.8 meters per second. So 9.8 times, it's just a constant. Okay, so the function final minus the function initial. So that means like the final height minus the initial height, or the height now minus the height 1 second ago, or 1 horizontal meter ago. So it's going to be that is going to be B3, sorry, minus B2. And then we're going to subtract from that 4 over 7 times the force due to gravity, which again is 9.8 times the absolute value. To locate absolute value, go math 2, where is it? Math 3, might have been in math 1, where was it? There it is. Absolute value comes up as abs of the final heights minus the initial heights, close bracket around the abs, and then that final close bracket is around the overall square root. If I hit enter, you can see that the way it's typed it out is it's raised this whole thing to the power of a half, which is the same as a square root, but that would be how you would do it. Now, like I said, you only have to do this once, because once we've defined it once, we're going to use the fill down function to fill it down for the rest of the values. So let's go fill range all the way up to C25 and hit OK. Okay, so we're not going to have to type that horrible equation anymore after this. Now, let's sort of have a think about what we've just done here. So column A is the x-coordinates of this parabola over here. Column B is the heights of that parabola, so the corresponding y-coordinate. And column C is the velocity of a cart at that x-coordinate. So when x equals 0, before the cart has started moving, it's traveling at 0 meters per second. 1 second in, it's now traveling at 5.8 meters per second. The velocity continues to increase, and you can see when x is equal to 20, the height is 0, the velocity is now maximum, so it's gone up to 18.7, and after that point it starts to slow down. So we can see it starts to slow down. Like I said, we're going to need the velocity of the cart to be no more than 5 meters per second at its maximum. So let's we need to keep going a little bit. So the cart's still traveling too fast. We're not just going to cut it off right at 23. We need to go a bit further than that. So let's just continue this. We're going to define the next cell as being equal to the previous cell plus 1. So we can repeat what we did before. In fact, we can just click on this cell above, go edit, fill range. Notice it already fills in the formula for you. So that just saves you a bit of typing. And we want to go up to a, say, 35 this time. All right, so that keeps going with the pattern, adding 1 each time. Let's do the same thing for the heights of the parabola. So I'm going to go edit, fill range all the way up to B35. Hit OK. And there we go. It's adding in the heights all the way up to, this time, 33, because the first couple of cells were taken. And we'll do the same thing with that horrible equation that we don't have to type out anymore. We just go edit, fill range, and go all the way up to C35 and hit OK. All right, there we go, all the way up to that value there. We're still traveling a bit too fast, so we're actually going to have to keep going a little bit more. That's fine. Fill range. Let's go this time up to, let's say, A40. All right, let's do the same thing over here. Fill range all the way up to B40. All right, and then in this case over here, edit, fill range all the way up to C40 and hit OK. There we go. Now we can see here that we encounter an error right here, because what's happening here is we're now taking the square root of a negative. So notice this formula here has a square root in it. So if the number inside the square root's a negative, the calculator is going to say error. That means it's fallen below 0. We don't want the velocity to be falling below 0. We want it to be getting as close to 0 as possible. So we want the roller coaster cart to slow down and not quite reach 0. So let's see if we can figure out where is the point where it actually reaches 0. Well, it's somewhere between 34 and 35. If I just change this cell here to 34.5, notice that immediately affects the corresponding y-coordinate, because it's taking that cell 37, putting it into the equation and giving us an output of the height, which is 13. And now we can see that the velocity is now below 5 meters per second, which is our acceptable range. So we could keep going. We could go here 34.7, let's say. That's not. That's now 3 meters per second. We could try and find exactly where is the point where the velocity reaches 0, or as close to 0 as possible. So for example, it falls below 1 meter per second when we put in an x value of 34.9. So that's at the point up here. So 34.9, somewhere over here, the velocity of the cart is basically 0. And when we get to 35, it's starting to fall back the other way. But like I said, we only need to get somewhere that is probably just like a little bit below 5 meters per second. That's acceptable. So that occurs at this point here. When x is equal to 34.5, we have a height of 13 meters. The cart is traveling at 4.34. So what that tells us is that we don't want our maximum here to be any higher than 13 meters above the ground. In fact, we want it to be roughly around 13 meters above the ground. So what does that tell us? Well, that tells us that the coordinates of our vertex need to occur at 38, which is the midpoint of those two neighboring vertices, like I said earlier. And the height needs to be 13, so or around 13. So going back over here, in fact, we could just type this in here as, to show you what I mean. What we're saying is that P parabola 2 needs to be equal to some constant a times x minus 38 squared plus 13. Put in a slider for a, and of course a is going to be negative because it's going to be a downward facing parabola. It's going to be somewhere around here, right? And what we need to find now is what is the value of this a that makes these two parabolas line up, which is to say we want the parabolas to be tangent with one another. So again, there'll be a bit more scaffolding in the task to say, okay, next thing, once you found this parabola, figure out the value of a that makes these equations tangent, and also figure out the coordinates at which the two parabolas would overlap. So that's what we need to do now. So I'm going to jump back to the main calculator screen to do this. So we now know that parabola 2 has an equation. We knew that the horizontal location of the turning point was 38, and now we know that the vertical point needs to be about 13 meters above the ground, such that the roller coaster is going to approach a velocity of 0 at that point. If I hit an enter, we don't know what a is, so we're going to need to develop a system of simultaneous equations to solve for a. Now, at the point where the two parabolas would be tangent to one another, by two parabolas, I mean parabola 1 and parabola 2. At that point, their y coordinates need to be equal, and their gradients need to be equal. So that is to say, they need to be smooth and continuous at that point. So we need to define the equation for the gradient at this point, the derivative. So we go d dx of parabola 2 at this point. D dx is equal to this equation here. And we're going to call that, so let's say define that as derivative 2, just to keep the naming conventions simple and easy to remember. Derivative 2, okay, we've defined that as the second derivative, and now I'm going to set up my system of simultaneous equations, and what I'm trying to solve for is the value of a that makes these parabolas tangent, and also I want to find the x-coordinate at which the two parabolas intersect with one another. So in other words, I'm trying to solve this simultaneous equation set for x and a, the two unknowns. So the way we can write this out using the CAS is to go here, and we can say we're trying to solve parabola 1. When is parabola 1 equal to parabola 2? Which is to say, when are the two y coordinates the same? When are they continuous with one another? And where are they smooth? Which is to say, where is derivative 1 of x equal to derivative 2 of x? Solve a and x. There we go. There are the a and x values. So what do these values mean? Well, first up, let's go ahead and show you using Desmos. What this is telling us is when a is equal to negative 13 over 116, we can see that these two parabolas only intersect each other once, and hypothetically they should have a gradient that is equal at that point. So that causes this point here to be a point of inflection, which is what we want. Okay, so we've got that point there. So that tells us that we have now figured out what the equation of parabola 2 is, which is fantastic. You're well on your way to getting a good grade here, and maybe during the SAC, some people will only get up to this point, but that's fine if that's as far as you get. That's still better than nothing. So it means that you've defined the first 3 parabolas, which is fantastic. Because this is very time consuming. So we now know that the equation for parabola 2 is this equation right here. So parabola 2 is negative 13 over 116 times x minus 38 squared plus 13, because 38 38, 13 is the turning point of this parabola. Awesome. And we now know that this x-coordinate, x equals 284, that's where the intersection occurs between these two parabolas. So just to show you that, if I was to type in parabola 1 with an input of that, we get this value here. And we need to redefine parabola 2 because parabola 2 should have this as its a value. So let's go back up here. So the equation for parabola 2, let's just define it. So we'll go action commands define. We're going to define parabola 2 as being equal to negative 13 over 116 times x minus 38 squared plus 13. So if I was to type in parabola 2 with an input of this same value here, we can see, parabola 2 with an input of this x value, which our system of simultaneous equations spat out before. There we go. That gives us the same y value that parabola 1 gave us, which is to say that the coordinates of the point of inflection, which you would need to label in your graph, occurs at the coordinates 284, 9, and 676, 81. So going back over to the graph here, let's just locate that coordinate. And I'm going to label it on the graph because it's important. So this is the coordinate 284 over 9 and 676 over 81. There it is right there. We label that point. All right. And good news for you is that as we can see here, because this second parabola, parabola 3, has the same width as parabola 1, and because this parabola is symmetrical, then the corresponding tangency point that occurs with parabola 3, will occur at the exact same height and the same distance from the first turning point. So to find where the coordinates of this point here are going to be, we need to remember that the turning point of this parabola is occurring at 38, 13. So that's an x-coordinate of 38. So if we go 38 minus the x-coordinate of the point where these first two parabolas intersect, that's a distance of 58 over 9. And what we can do is go 38 plus 58 over 9. That's going to tell us the x-coordinate of this second point here. And sure enough, if I was to type in, say, parabola 2 with an input of 400 over 9, that is the same y-coordinate as that first one. So we can just label that second point 400 over 9, 676 over 81. That's the coordinate where these 2 points, parabolas, are intersecting one another. You would label that point on your graph. I'm just using Desmos to label it clearly. I'm not doing any calculations using Desmos. You can see everything is happening using the CAS. All right, so that's fantastic. Now we actually can start to define our piecewise function, because parabola 1, we can see here, parabola 1, we want that to go all the way down to here, and then we're going to switch over to parabola 2. So where are we switching over to parabola 2? Well, that's that x-coordinate that we found before. We're going to go from 0, x, up to this coordinate here, which was, what was it again? 284 over 9. 284 over 9, that x-coordinate there. That looks pretty good. We want our parabola 2 to be defined from an x-coordinate of 284 over 9 up to this other point here at 400 over 9. At 400 over 9, that point there. And we want our parabola 3 to be defined from 400 over 9 up to, well, we don't really know where we're going to go up to yet, but that's as far as we've gotten so far. So again, like I said, if you just defined up to here, then you've done pretty well so far. We've defined at least part of the roller coaster, and we've used our CAS calculator. We've used that formula before. Just as a quick aside, what's the point of this component of the SAC? Well, it's really got to do with how well you can use your CAS calculator. This is outcome 3 of the study design, which is all about technology use, and that is what this SAC is all about. You can see we're doing a lot using the CAS calculator, using spreadsheets, defining, solving systems and equations. Pretty hard to do this by hand. All right, so let's start to define our piecewise function. If we jump back over here, we can now say, okay, what's our piecewise function looking like? Well, we have, let's call it y is equal to p of x is defined as a bunch of different things. So let's say y is equal to p of x is defined as, for the first part of its domain, it's defined using that first equation that we found before, 1 over 16 x minus 20 squared, 0, and that's defined from 0 right up until a value of, what was it again? The point where the first two parabolas intersected was 284 over 9. The second parabola was given by an equation of, what did we write down before? Negative 13 over 116 x minus 38 squared plus 13. That is defined from 0 to 4 over 9. So from 284 over 9 up until, so from x is greater than that value and less than 400 over 9 was what we had before. And next up we come to the third parabola, which was 1 over 16 x minus 56 squared, from 400 over 9 up until we don't know yet. So this is as far as we've gotten so far with our piecewise defined function, but this is how you would be defining your function in your SAC, like using this kind of notation. So piecewise definition. All right, so let's continue. Where are we up to so far? So recapping our process so far, our roller coaster has come down here. It's gotten up here, and hypothetically, it should now slow down to a pretty slow speed before speeding up again. What is that pretty slow speed? Well, we've defined parabola 2, so we can now actually figure out what the velocity is using the spreadsheet function as the roller coaster continues along this track. So if I jump back across to the spreadsheet function, we go across to the third column over here. Where have we gotten up to? So at this point here, 34.5, on the parabola 1, we had this height here, but we're no longer traveling parabola 1. We're only traveling on parabola 1 up until that point where the two graphs meet. What was the coordinates for that point again? Oh yeah, it was this one here that we found before, 284 over 9. And as you can see here, that's approximately equal to 31.555. So we don't care so much about the velocities beyond this point anymore. So we can kind of get rid of them. And we just want to consider, what is the velocity of the cart right before it transitions over to traveling on top of parabola 2? So at that point, we have an x-coordinate of 284 over 9. There it is. That's the x-coordinate where we transition from one parabola to another. Just to confirm that, if I type in here equals parabola 1 with an input of that, we get that value there. And if I put in the exact same value on the next point down and type in equals parabola 2, because I've already defined parabola 2, just remember, using the command function, we can see it gives us the exact same y-coordinate at that point. Y-coordinates are the same at either point. Awesome. So that means that we can continue the process before. So let's just go to the next x-coordinate. So x equals 32, so a little bit further along here. And we're going to keep going. So 33, well, we want to save time. So let's go equals. We're going to fill, let's go here, edit, fill, edit, fill, not liking it so far. Let's go here, edit, fill range. Okay, we want A37 to be equal to A36, the previous cell, plus 1, and we want to repeat that process up to, say, A50. There we go. So keep going up there. All right, and we want to figure out what is the corresponding height at each of those points. So if we go equals parabola 2 with an input of 32, what's the height on parabola 2 at that point? When x equals 32 on parabola 2 here, parabola 2, let's find the point. Somewhere around here. 32, y is equal to 8.96. That's what the spreadsheet is telling us, and that also lines up with what Desmos is telling us, so that's the height. The next one is equal parabola 2, an input of that. Well, let's save ourselves some time. We can go edit, fill range. We want that formula. B37 is going to correspond to A of the same number, parabola 2 with an input of A of that same number. We want to repeat this process up until B50. And there we see all of the corresponding y coordinates. Now, as another aside, what you can do if you want to visualize what we've actually got so far, if I highlight these first two cells here and go graph scatter, that shows us a scatter plot of the heights that we have found so far on the CAS calculator. So that's where we're up to so far with our little diagram over here. Also keep in mind that we are going to stay on parabola 2 up until the coordinate, 400 over 9, which is 44.4444. So we only want to go up to just after 44 here. So let's just type in 44 over 9, and we're going to get rid of those two here. Okay, so this is going to be 400 over 9. Just confirm that if I was to type that into parabola 3 with an input of 400 over 9, we get the same y value, which does line up with the fact that that point is a tangency point between those two parabolas. All right, so we're interested now in what's the velocity at the maximum here. So the way we can do that is, again, we've already defined the equation that we're using, so we can just go edit, fill range on column C, go all the way up to C50, hit OK, and we can now see the velocities at these various points, and in particular, at the point where x is equal to 38, we can see that the velocity has now dropped down to 4.7, so that is below 5. Look, it's fine if your velocity at the turning point is like a little bit above 5. That's all good. I don't expect you to go back and redo everything all over again, but just be aiming for that sort of speed just to show that you're kind of considering this factor. So the velocity is at an acceptable place, and then it starts traveling down the other side. Beautiful. All right, so now we're back over here. The velocity is now 9.35 at the point of tangency here. We need to now consider what's the velocity when it's traveling on the third parabola. So we're now going to switch over to considering parabola 3. So let's go up to, we've got 44.44. Let's go to 45 as our next cell, and then 46. And again, we can just go edit. Well, it's going to be equal to the previous cell, to be equal to the previous cell plus 1. We can use that as our formula. If I go edit, fill range right up to, let's say, A65, repeats that same method all the way up to there. And if I was to define each of these ones here as being equal to parabola 3 with an input of the neighboring x value, we can repeat that process again. We go edit, fill range all the way up to B65, and that shows us the corresponding y values all the way up to there. So now where are we up to? We're up to a height of 0 point something when x is equal to 59. We're going to need to go a little bit higher because we're not expecting the cart to reach 0 until it's probably gotten around here. So let's keep going with that. Let's go edit, fill range. This time maybe we'll go up to cell 75. And we'll do the same thing here, fill range up to B75. What's the velocity at that point there? Let us have a look at that. So if I go back over here and go edit, fill range using the formula for velocity that is already defined, fill that one up to cell 75. Let's have a look at how we're tracking so far. So what we've got right now is we've got the roller coaster traveling down here, starts to go up here. It's probably going to reach its maximum velocity at 56.0. Let's double check if that's true. So 56.0, the velocity does seem to reach a maximum. It was 14.26, and then it went up to 14.29, so that's a little bit higher. And then it starts to slow down, and it seems to reach around 0 after 67. And at x equals 67, we're already seemingly below 5, so that's all good. So that tells us that we want our height to be, it looks like about 7 meters above the ground should be acceptable. So yeah, the height of our next parabola, which is going to be around here, is going to be 7 meters above the ground. So let me show you the process that I go through to find the coordinates, to find the equation of that parabola once again. So earlier on, like I said, we've put down these two vertices or turning points of these two parabolas that are the upward facing parabolas 56 and 84. So the coordinates of the turning point of the parabola that is in between those 2 points must be at the midpoint between 56 and 84. So what I'm going to do is to find the midpoint of those 2 points, we're going to go 56 plus 84 divided by 2. So that is x equals 70. That tells us that we want our turning point to be located at the coordinates x equals 70, and we've said over here that the height should be about 7 so that the roller coaster doesn't completely slow down but isn't going too fast. Okay, so that is going to be our minimum. That's what we found. So our maximum turning point there. All right, what does that tell us? Well, it tells us that the equation of parabola 4, that's what we're up to so far, is going to look like, and we've run out of space over here, but it's going to look like something like this. We don't know what A is, so we'll just put A, but the x coordinate of the turning point is at 70, so it's going to be 70 squares, x minus 70 squared plus 7. Okay, so the coordinates of the turning point occur at 77, so in the form ax minus h squared plus k, h is equal to 70, k is equal to 7. All right, let's jump back over to our screen here, so to continue visualizing what we're trying to do. All right, now what would that equation look like? Well, we've just written it out, but we can define it using the CAS calculator. If I go back to the main screen here, we go action, commands, define, and we're going to define parabola for x as being equal to a times x minus 70 squared plus 7, hit enter. You've already seen me do this before, but this is just a recap. Then we're going to find the derivative of that function because we need the derivative to find the point where this parabola 3 and parabola 4 are smooth and continuous. So we're going to have parabola 4 x, and we're going to define that derivative as, say, derivative 4 is equal to that equation there, and that's what we're going to use in our system of equations. So to show you what we're doing here, we're trying to find what is the value of parabola 4. So we don't know what a is, but it looks like x minus 70 squared plus 7. Plus 7. We've got our slide of A here just to help you visualize it. There you go. We're trying to find where are these two parabolas going to be tangent with one another. It's going to be somewhere around here. So smooth and continuous. We want to find where are the two derivatives equal, where are the two parabola heights equal. We're trying to solve for A, which is the this value that's at the front here, and also X, which is the X coordinate at which the 2 points are going to intersect with one another. So we set that out as a system of equations just like I did before. And we want to find where is parabola 3 equal to parabola 4, and where is derivative 3 equal to derivative 4. We solve for a and x. It tells us x is equal to 64, a is equal to negative 1 over 12. All right, so let's type that in over here, negative 1 over 12. That is the a value, and the coordinates of the intersection is going to be x equals 64, and what's the y value? Well, let's plug that into, say, parabola 3 with an input of 64. The y value is 4, so the coordinates of the two intersecting one another, that will occur at 64, 4. All right, that's that point there. And that is also going to be tangent with the second parabola at an equal distance from the turning point. So we can see that this first point of tangency occurs, so the difference between 70 and 64 is 6. So the next one's going to be 70 plus 6, and it'll be at the same height as that first one. So it's 76, 4. So we may as well just label that on there as well. So 76, 4 is the point of tangency between parabola 4 and parabola 5. All right, so once again, we've got what we need to continue defining our piecewise function. What we now know is that a is equal to, what was it again? Negative 1 over 12. So a is equal to negative 1 over 12. And this is we're going to transition from parabola 3 to parabola 4 when x equals 64. And we're going to start this from x equals 64 up to, well, do we know that yet? Well, we do actually, because we're going to transition from parabola 4 to parabola 5 at this point here, 76. So we can define that up to 76. Our piecewise function is looking pretty good so far. So let's see if we can finish this one up. So that's what we've done. We've come up to here, we've come down here. All right, and let's just define everything using the software to make it look nicer. But again, you would just draw this, erasing the points of intersection, so that we just have our piecewise defined function without these lines coming out here. So we want parabola 3. We want parabola 3, where did it go? There it is, to go up until 64. And we want parabola 4 to go from x equals 64 up to x equals 76. And then our fifth parabola is going to go from x equals 76 up until some unknown value, which we'll get to in a minute. So let's jump back over to the spreadsheet function to see how we're going for velocity. So again, down here, we're so far up to 60. Well, where did we get up to? So we transitioned from parabola 3 to parabola 4 at x equals 64, so we can get rid of everything below that. Now, at this point, when x equals 64, we just need to quickly double check. When I put in 64 into parabola 3, I get 4. If I put in that into parabola 4, what do I get? I should get the same value. Oh, I think I forgot to define parabola 4. If we go back to the main screen, we need to fully define parabola 4. Yep, so currently parabola 4 is just defined as this. So we now know what a is, so we can put that in as our a coordinate here. And just remember to do what I'm doing here. You can go edit, copy, edit, paste. And if I hit enter, and if I jump back to the main screen, spreadsheet function, jump back down to 64. Hopefully you're seeing how annoying it was that I lost all of this progress before, but there we go. We're up to 64. 4 is a point that occurs on parabola 4 as well. All right, so we're going to continue this process of we're up to here. We want to continue along this parabola here and see what the velocity is at those various points. So we've got our equation defined already, but we want to keep going. So let's say we go all the way up to 76. So we're going to go from 64. We're going to go, this next cell is going to be equal to the previous one plus 1. We want to repeat that using the edit, fill range right down to let's say 85. That's overshot it by a little bit. That's fine. We'll just get rid of those ones. We want to stop at 74. So we'll define parabola. Each of these values here are going to be equal to parabola 4 with an input of this cell that's next to it. And we want to repeat that right down to 74. So we repeat that value there. We're going to go fill range down to A81, hit OK. What's happening here? So that caused an issue. Yep, so it should have been fill range, where it's just B84. So up to B81. There we go, that's better. So we've got all of the corresponding Y values for each of these X values on that purple parabola 4 facing down there. Let's consider the velocity at each of those points. Fill range. We've got that formula already typed out. We only have to type it in once, like I promised at the start. We type in C81. All right, there we go. So we can see, okay, this is perfectly acceptable. This is what I was saying before. So at the turning point, X70, Y7, the velocity goes down to 5.3 meters per second. It's not quite below 5 meters per second, but like I said, I'm giving you a bit of leeway here. If you're a little bit too fast, that's fine. This is within an acceptable tolerance. So maybe the instructions will say the velocity needs to be, so the maximum velocity at the maximum before we start going down needs to be no more than 5 meters per second. So that's perfectly acceptable. Yeah, and then we'll transition to the last parabola, parabola 5 at this point when x equals 70, 76 should be. So we need to go 75, 76. Okay, let's fill this down to 76. Edit fill range to B83. There we go. And do the same thing with this one. Up to C83. All right, that's better. So it's at this point when x equals 76 that we transition over to parabola 5. So let's do that. So we type it in again. 76, we have this is equal to parabola 5 with an input of 76. Yeah, so we've already defined parabola 5 earlier. That was up here. So 1 over 16, it's got the same width as parabola 1, and it has its vertex at 84, 0, so that's its equation. So again, now we're back over here. We need to figure out at what heights are we going to reach a maximum. By now, we now have 5 parabolas. The instructions were that you need to build the roller coaster with at least 6 parabolas. So we're going to have one more downward facing parabola, and then you can finish your parabola doing something like just having like a straight line function. So if I go back across here, that's how I finished this one before, which is actually the exact same parabola that I'm building right now. We want to have like a parabola that ends with its turning point, and then because the gradient's 0 at that point, we can just have a straight line, and then that gives time for the roller coaster to just slow down, and then there can be a stretch where it slows down and reaches the stop there. If you have time, you can keep going, but as you can see, this is a very time-consuming procedure, so that's fine. So let's just figure out where will that parabola occur at. So first up, let's figure out at what height are we going to be able to reach before we can't go any further. So let's consider we're going to need to keep going up to at least 84, probably somewhere up to like maybe about 90 or so. So let's just go ahead and do that. We're going to want to define each of the x values as equal to the one above it plus 1. And we go edit, fill range right up until 100, let's say, and we want to keep typing in parabola 5 with an input of the neighboring x value up until B100. Hit OK, beautiful. And then over here, we want to continue going on with the formula for velocity up until C100. All right, so there we go. We can see that the parabola is going to reach its maximum velocity at that coordinate, which is the turning point of this parabola, 84, 0, reaches a maximum velocity of 11.22 meters per second, and then it starts to slow down, coming up to here, and it, like it's almost reached below 5. Let's just got one more coordinate, so we want to fill this one down. We want to fill this one down. Okay, so it does fall below 0, somewhere around there. Let's try 92.5. So at x equals 92.5, we have a height of 4.5 meters. So that's up here, 92, 4.5, something around there. And the velocity at that point is 3 point something meters per second. We can probably try and get a little bit closer to 0 because this is the end of the ride. So let's say maybe at that sort of velocity, that sort of height at about 4.7, we're pretty close to 0. We get any closer. Okay, there we go, 4.8. Let's use that as our final height. So we want the final height of our roller coaster to be about 4.84 meters above the ground. So 4.84 is the height of our final turning point, and we can sort of eyeball the graph here. We can decide where we want the vertex to occur. So maybe we want it to occur somewhere like a little bit further over here. So it could be like at 94, x equals 94, y equals 4.8, but you could define it, just needs to be somewhere that's a bit larger than this x coordinate here. So maybe 94, 95, for the x coordinate of your turning point. I'm going to say that I want to locate the final turning points at, let's say, 95, 4.8. So that can be that's the vertex of my final parabola that I'm going to define over here. So that means that this final parabola is going to be, well, we don't know what A is yet. It's going to go for the coordinates of the turning point are going to be 95 squared, so 95 and 4.8. Okay, and we know that this is going to start, this parabola is going to begin at what coordinates? So jumping back over here, it's going to begin, well, we haven't figured that out yet. All right, well, first up, what have we got here? So first up, we have, oh yeah, we haven't added in parabola 5 into this piecewise defined function yet. So let's go back to that. All right. So the parabola 5, that had the equation 1 over 16 x minus 84 squared. That was from 76x up until unknown. So where are we transitioning from parabola 5, which was this parabola here, to parabola 6, which is the final parabola. So to locate that, we're going to do that same thing with the smooth and continuous properties one final time. So we go back to main. I'm going to first define parabola 6, just like before, as being equal to, and again, we don't know what A is yet, so x minus 94 squared plus 4.8. To visualize what I've just done here, this is what the parabola looks like, is equal to A of x minus 95 squared plus 4.8. And we're now just trying to figure out what's the value of A that's going to make this smooth and continuous with parabola 5. So to do that, we're going to need to go, back to keyboard, define ddx of parabola 6. There we go. And we're going to go define derivative 6x equals to that. There we go, define that. Where are these two parabolas smooth and continuous? Let's set up our system of equations as before. At what point does parabola 5 equal parabola 6? And at what point are their derivatives or slopes equal to one another? Solving for a and x, hit OK, there we go. It's at those particular coordinates. So that means that a needs to be equal to negative 24 over 221. That looks good. And this intersection occurs at x equals 5004 over 55, which occurs at the y coordinate. If I just plug this into, say, parabola 5 or parabola 6, should give us the same value. We need to first redefine parabola 6. So we need to redefine parabola 6 as being equal to what it is. I'm going to need to change what the value of A is, because now we know what A is. We can plug it in there. Boom. Define that. Invalid syntax. We've got the 4.8 at the end there. There we go. If I plug in that same x value into parabola 6, do we get the same y value? Yes, we do. It's the same y value each time. Beautiful. All right, so that gives us the y coordinate of the point of intersection between these two parabolas. So let's just label that on the diagram. 5004 over 55 and 9216 over 3025. That's that point right there. All right, beautiful. So let's just redefine this to Well, okay, so let's put this into our system of equations. That point there, 5,004 over 55, is the point we're transitioning from one parabola to another. So we can type it in, 5,004 over 55. And then we're going to switch over to parabola 5, which is negative 24 over 221 x minus 70 squared plus, not 70 squared, sorry, it's x, so x minus 95 squared plus 4.8. It's going to be that final equation from the value 5,004 over 55 up until, and we're going to go up until the vertex of this parabola, because then we're going to transition to a straight line for the last part of its domain. So its vertex occurs at 95, 4.8. So that's the x-coordinate that we're going to terminate this one as 95. All right, and the final stretch, it's going to transition across to a straight line. So from x equals 95 up until, let's say, x equals 100. That seems like a nice round number to finish things on. We're going to have a straight line, and that straight line is just going to be 4.8. And of course, the derivative of the constant 4.8 is equal to 0, and the derivative at the turning point is also equal to 0, so this will automatically just be smooth and continuous at that point. So let's just go ahead and type that in here. So from 5,004 over 55 up until the turning points at 95, we've got that parabola. Parabola 4, sorry, it was parabola 5, there it is. Which one is this? Yeah, parabola 5. That one went up until 5,004 over 55. And then finally, this after this turning point here, we're just going to transition across to a straight line. So our line is simply equal to 4.8 from 95 up until x is equal to 100. There we go. So that's our final little part at the end there. Beautiful. All right, so let's now just consider what is happening to the velocity of this cart at each of those points over there. So if we jump back over to the spreadsheet function, we can now finish things up. We've got everything defined. So where are we up to so far? We're up to 92 points. Okay, so we need to go back here at the point where we transition from parabola 5 to parabola 6. That was 5,004 over 55. That is approximately equal to 90, so let's just type that in. So this is 5,004 over 55. How fast are we going? Well, we seem to be traveling at about 7 meters per second at this transition point here. Then we transition over to parabola 6, so at the point 91 and above. So, well, actually, let's just redo that point again. So if I plug that into parabola 6, do we get the same value? Yes, we do. Okay, so the velocity at that point should be the same. All right, so now we've transitioned over to parabola 6. We're going to go starting at 91 to just keep things nice. And then the next one is going to be the previous number plus 1. We're going to keep that going up until 95, which is when we transition over to our straight line. Edit fill range down to let's say a 106 or so. That should be about right. We need to go a bit higher. So 97, 98, 99, 100. All right, so it's up to cell 110. We'll do the same thing for this thing here. We want the height of parabola 6 with each of these inputs. So we go edit fill range down to B110. Those are the corresponding heights of the parabola. Is this right? So we've got parabola 6 at we only want to go up to x equals 95. So that's the maximum, 95, 48, 4.8. So that's where we would go up to. And then finally over here in this cell here, we're going to figure out what is the velocity up to the maximum. So we go edit fill range down to C105. There we go. So we can see at this point here, at this maximum, the cart is now traveling at 2.24 meters per second. And it's at that point here that we are now just going to transition across to our straight line. So, for example, when x is equal to 96, y is equal to, well, it's just still equal to 4.8. And in fact, it's always going to be equal to 4.8. So 97, 98, 99, 100. Cell's always just equal to 4.8. So how does this affect the cart speed? Well, it seems to just continue traveling at the same speed from then on. But we can imagine that we could have like some brakes in place to slow things down. Done. So that is our overall roller coaster. So let's see how we can analyze this now using the CAS calculator. First thing you could do is you could highlight these two first columns, go analysis, go graph, scatter. You can see what the roller coaster looks like in terms of its height over different points. If we highlight just columns A and column C, we could also graph the so graph, scatter, we can graph what the velocity looks like. So this is some stuff that you could analyze when you've completed your graph. You can talk about how the velocity reaches a maximum here. What is that maximum? Well, we can analyze this. I think we can go and play around with this yourself, but it would be, I think if you just click those points, we can kind of see how high it is. I mean, I guess you can label this for yourself. You know that the maximum is going to occur at the corresponding minima here, but this gives you a nice little graph that you can talk about in your analysis, basically saying that the velocity reaches a maximum at each of the minima of the height graph, because that's when the cart's traveling fastest before it starts slowing down again. All right, so that is from beginning to end how you can design your own roller coaster. It's a very lengthy procedure. So, like I said, it depends on how far into it you get when you're making your parabola. When you're making your roller coaster, maybe you're only going to get up to the first couple of parabolas in the 2-hour window that you have to work on this. That's all good. I just want you to show me that you understand what you're doing, I guess. Write in a bit of an analysis about what you've done using the CAS calculator to explain your method, even if it's exactly what I've done in this video. That shows that you are able to use your CAS calculator and the spreadsheet function and the define function and the simultaneous equations function on this. Visualizing things using the scatter function there is also really good to talk about. And also a bit of an analysis of how the velocity is varies across the domain of this roller coaster ride would be good as well. And then, if that's something that you're completely fine with, you can continue reading through this document here, where it then goes into a bit of detail about other forces, the force of friction, the static friction. That's all definitely extension. But like if you still have time in the sack, feel free to go down that sort of route. At the end of the day, what I'm hoping to get out of everyone is essentially something that looks like this. Once again, I'm going to give you different initial conditions. So it's not like you can just copy this into your theory book. I'll give you a different initial height and a different initial slope. But the procedure that you would use is exactly what I've described in this video here. So the SAC will give you a bit more of a breakdown of how to do this step by step. To scaffold you a little bit, this is what you will be doing, exactly this. The points that you need to label that are significant in your diagram, well, of course, you'll need to write in that y is the height and x is the horizontal position of the roller coaster. You'll need to label the intercepts, which are also the turning points. You'll need to label these points here where the points of tangency between the various parabolas and any other points that you think are significant. They're really the most important points. And then finally, you could then graph over the top of this a rough drawing of what the velocity looks like. Remember to define any values that you put out. If we're talking about velocity, make sure you use meters per second, everything like that. And yeah, just explain what you've done. You don't need to use too many words because I want you to have time to make something like this, but you don't want to repeat yourself over and over again. But I also need to know what you've done for the marks associated with use of technology. So keep that in mind. And to be honest, you wouldn't have been able to do this without technology anyway. So if you've produced something that looks like this, and I'll check to make sure everything makes sense. But then you've shown me that you know what you're doing. But yes, define your procedure. All right, so that's all for this video. Thank you very much for watching. It's a very long one, but yeah, thank you if you watched the whole thing. Thank you for sticking with me to the end. I'll see you guys soon. Have a good one.